So the current is leaving the voltage source, entering R1, and then point X before it diverges into some going to Y and some going to R of 4. And then the current that goes through Y will complete a clockwise circuit, and then it will recombine with the current going through R4, and they will recombine back into the full current, which is at Z. So in that case, the I of X is equal to the I of Z, because they both have the full current, and it's getting more than the current at point Y. So I will give 1 for X, and I will give 1 for Z, but 2 for Y. Okay, and we're going to say that the current at point X is out of the battery, X, before it reaches the junction and splits. A current at point Y is not the full amount, as some current went to R4. Then current at point Z is the full current, as it's going back to the battery. Okay. Now, resistor 4 is removed and replaced with an uncharged capacitor. And at time Tx, the switch is closed at position X. Then after some time, the capacitor gets fully charged, and then at some point, time Y, the switch gets closed at position Y. So let's just analyze what's happening. So if we're talking about time of X, we only have R1 getting involved, right? But if we talk about time Y, we have R2 and R3. Okay, let's also analyze some stuff. So at time X, when the switch was just closed, the capacitor is not charged. So the voltage of the capacitor is going to be 0. And the R1 gets the EMF of the battery. Yeah. But then at time Y, there is no battery in the circuit. And so the voltage, so basically the EMF is from the capacitor, which will now discharge. As it discharges, and it will give current to both R2 and R3. Okay, so in both circuits, the current is not 0 in both circuits. Okay. All right, so B, express your answer to part BI and part BII in terms of numerical values, EMF and R only. So you see here they said immediately after time Tx. That means that the capacitor did not get the time to charge yet. So that means that we're going to say V is equal to IR. That's just Ohm's law. And V being the EMF in the figure. And IX, that means the current at time X or at position X. And we're going to be dealing right now with R1 only when the switch is closed at point X. So times R1. Now right here that R1 is equal to 8 ohm. And so now we're going to say IX is equal to EMF over R1, which equals to EMF over 8. Okay. Now immediately after time Y, the current position Y is IY. Do I have an expression for IY? Well, time IY here, as you can see, there is no battery in that circuit, but the capacitor was already fully charged. So now the capacitor is going to discharge. So now the capacitor got fully charged, and now it's going to be carrying the voltage of the battery, and that will be equal to the IY R2 plus R3. Yeah. Okay, So EMF is equal to IY. Instead of R2, put R. Instead of R3, put 3R. So IY is equal to EMF over 4R. Okay, that's basically how it works. Yeah. So that's going to be our work for part AA. Okay. So obviously the current IX will be less than the current, this is, sorry, just 4 ohm, was it? It was 4 ohm, yeah, so just 4. Okay, because, 1 second. Yeah, wait, actually, this has to be 8R. It's going to be R, okay? Because we don't have a number. They just called it, like here they called R1 8R. It's not 8 ohm. Okay. So now, they're saying, so now just looking at it, which one do you think is more? IX or IY?
IY.
IY is more, exactly. Yeah. It's more than IX. Good. On the grids provided, complete the bar chart for each resistor immediately after time X. So look, in the circuit at time X, we said that we only had R1 being active. So only R1 can get a power. But the R2 was a 0. So we'll put a 0 here. Yeah. There I'd actually put this thing. So put 0 here and put this here. And actually at time Y, the R1 was not part of the circuit. We're going to put a 0 here. But R2 and R3 must have a power to a certain extent. So look, right now, if you look here at the scaling, having two scale units is equal to power 1. So 2 scale units is basically power 1. The question is, what is power 1? So we're going to say power is equal to I squared times R. And the I in time X was was EMF over 4R, correct? If you recall. Actually 8R.
Yeah, 8R.
We square it, times it by R. EMF squared over 64 R squared. Oh, and the R is how much? It's 8R, right? And let me just bring the figure. Yeah, you see, it's 8R at time of X. So instead of R, put 8R. So times 8R. And now remove the R with this square. So we'll get EMF over 8R. So EMF over 8R is equal to 2 bars.
Okay.
Are you confused?
No.
Okay. And now here we said that the IY was equal to EMF over 4R. So let's talk about R2. We're going to say power is equal to I squared times R. And so EMF squared over 16R squared times, and R2 is just an R. We'll get EMF squared over 16R. So which one is bigger, EMF over 8R or EMF over 16R?
Wait, mister, so this R is supposed to be the total
R? No, I'm doing R2.
Oh, okay.
R2 is just R.
Oh, okay.
So which one is more, EMF over 8R or EMF over 16R? 8R, exactly. So if this is 2 bar units, this one is going to be 1 bar unit, right?
Yeah.
Like this. Okay. Now that's good. And now let's do the same work for what? For R3, which we know is 3R. So now we're going to say EMF squared over 4R over 16 R squared times 3R. EMF squared over 16 R. So now which one is like this is 1 over 8, this is 3 over 16. Which one is bigger?
1 over 8. No, 3 over 16.
By how many times bigger? Okay, if you don't like that, think about this guy here was EMF squared over 16R. This guy here is going to be 3 times that.
So it's 3 bars.
3 bars. Like this. And now we took care of it, right? Okay. Immediately after time x, the total instantaneous power dissipated by the circuit is Px. And after time y, it is Py. A student says that Py is equal to Px. Is that true or not? It's actually incorrect. You know why? Because if you look back here, we have 2 bar units for the entire Tx. Here we have 4 bar units for the entire Py, right?
Yeah.
So basically incorrect. Px is equal to, we can simply go back here and say it is EMF squared over 8R, while Py, go back and plus them, EMF squared over 16R plus EMF squared over, 3, 16R, which means 4 EMF squared R, which is EMF squared over 4R. So Py is bigger than Px.
Yeah.
Good. So look, here we have a power supply. That is your positive terminal and that is your negative terminal. So the current is essentially going to leave the positive and go and come back to the negative. Correct? Okay, so look, here we have a rectangular loop, but is the entire loop inside the magnetic field? No. So the bottom parts are not. They will not feel any magnetic force. But this part does feel a force. This part does feel a force. But the forces here will cancel out. Because the currents go in the opposite direction. And so the forces will cancel out. So what's going to be left? Only this part here. Okay. So now, let's just, so look, what it says here is that once the current is on, then the F scale is going to have a certain reading.
Okay.
And that reading is going to be the reading of the magnetic force, essentially. Because when a current passes through a wire, and the wire is sitting inside a magnetic field, the wire will be feeling, or the loop in this case, will be feeling a magnetic force. The question is, what is the direction of that force? So here we're going to be using a right hand rule, point the thumb to the right, the fingertips out of the page, and the palm is going to be pulling down to the bottom of the page. Do you get it?
Isn't it electrons? And
Current is current. It's always current in a wire.
oh, okay. Yeah.
So the thumb points right. The fingertips point out of the page. The palm will be to the bottom of the page. Okay? So now the magnetic force is going to be heading downward. But now they're saying justify your answer, so we're going to say that only the top part of the loop experiences magnetic force, and using right hand rule, so the thumb being to the right, the fingertips out of the page, the palm bottom of the page. But the bottom part of the loop doesn't experience
Any force.
any force. And I don't know if there's enough space, but and the right / left sides of the loop have a 0 F magnetic net. Okay. Derive an expression for R. So F magnetic is equal to ILB. Now EMF is equal to I times R. So I is equal EMF over R. So F magnetic is equal EMF over R times L times B. Now, here they said that the width of the loop is W. That means we have to replace L with W. And also, we said that earlier that the F scale was equal to F magnetic. So replace the F magnetic with F of scale. And so now R is equal to EMF times W times B over F scale. Yeah, that's how we do it. C, describe a procedure to collect data that could be used to graphically determine R by using the setup provided. Well, look, what can we control?
Damn.
The EMF, exactly. We can actually control the EMF. Okay. So we can actually vary that. Yeah. Let's go back. Let's fold back to this equation. So we're going to say F of scale because you can, read the F of scale.
Yeah.
That means it goes on the y-axis. Is equal to EMF times W times B over R. So here, the F scale is going to be the y, EMF is the x, and WB over R is the slope. Okay, so we can vary the EMF, get different F scale readings. We can do this for 5 times at least, and we can plot them, and the slope is equal to WB over R.
Okay.
So basically say, use a value of EMF and record the F scale. Do this for 5 different EMF values to get more accurate data. Yeah. EMF is the power supply, F scale is the scale. Yeah, this is good. It's a short procedure.
Yeah.
You must do it 5 different times at least to get more accurate data. So yeah. All right, good. So we did that. Another thing on the axis provided, complete this. Okay, so F scale, right? And this is going to be the EMF. Label the quantities. Sketch a line. Well, look, we're going to be expecting a straight line.
Yeah.
And there's no y-intercept, so it has to start from 0. Yeah. Describe how the sketch of the curve will be used to determine R. So we're going to say that F scale is equal to EMF times WB over R. So the slope of the line is WB over R. So R is equal WB over the slope. Yeah, that's about it.